Good morning, students. Let us start the class and let me start the module 3 now. This module 3, even though in the syllabus it is module 2, I covered the source encoding first so that it is easier for you to go through the fundamentals and then the source encoder. Later on, let us discuss about the channel encoder. That is why I have come to this particular module now. This module is called as fundamental limits on the performance of the communication system. Now you can see here, as I had discussed the block diagram yesterday, you can see here that the data communication channel is basically discrete and the coding channel is also basically discrete, whereas the modulation channel is analog. I had told in detail about why the modulation has to be analog. Whether it is a wired medium or a wireless medium, the carrier should be analog in nature so that its propagation will happen in a better fashion. Even if we use a digital carrier, it is actually going to become analog when it is passing through the communication channel because of the channel's own properties. So that way, we can see that the modulation channel is analog and there is a transmission medium, and in the transmission medium, noise is going to be added. In the wireless medium, more noise is going to be added, whereas in the wired medium, there can be a lesser noise. But even in the wired medium, there are noises that are going to be affecting the communication. You will be studying more about noise in the course called Analog Communication in this semester itself, where you will come to know about different types of noises that are affecting our signals. So, even in the wired medium, there are noises occurring such as switching noises, electrical noises. In the wireless medium, there are noises occurring such as the atmospheric noises, sometimes even the galactic noises, so on. So, the modulation channel is analog, in which there will be a noise that is occurring and the noise will be affecting our signal. Whereas you can see this coding channel which is discrete, that is involving this modulator and demodulator. Whereas including the channel encoder and the channel decoder, it is a data communication channel. You have to visualize the blocks here. Initially we have a information source, then we have a formatting, then we have a source encoder, then we have an encryption. All those things are before this channel encoder. I have not listed those blocks here specifically. Sorry. Because from now on, we are going to discuss only about the channel encoding and channel decoding. But you have to remember that there are preceding blocks here. Similarly, there are succeeding blocks after the channel decoder at the receiver. Now, from the channel encoder till the channel decoder, that is called data communication channel. And from the modulator till the demodulator, it is called coding channel. Both are discrete. And the transmission medium itself is the modulation channel, that is analog. Now, this is the transmitter. In between, there is a physical channel, and then there is the receiver. This is in general a specific block diagram for discussing the limits on performance of a communication system. Let me proceed further now. In between, if you have any questions, you can always put your questions in the chat box and I will try to answer. Now, impairments found in the physical channels. Please remember always that the physical channel is analog in nature. Okay, and in the physical channel only, noise is going to be introduced into our signal. So, the impairments found in the physical channels are, there can be amplitude and frequency response variations. When the signal passes through a physical channel, maybe it is free space, or maybe it is a wired channel, or maybe even if it is an optical fiber, there will be attenuation in any channel. We always say that even space will have resistance. That means space is also filled with a magnetic field, and any propagation of signal cannot simply pass through the free space as such. Just like the materials will have their own resistance or impedance, even the space will have its own resistance or impedance. Just to give you a real life example, now in between you and me, imagine that we are in the offline class and imagine that we are in the classroom. In between you and me, the space is there, and if the space is not having any impedance or resistance, then I need not raise my voice in the classroom, or I need not increase the amplitude of my voice in the classroom. Even if I whisper also, it must be audible to the first bench students as well as to the last bench students, right? Now, even if I whisper, it may be audible only to the first bench students. It may not be audible to the last bench students. Why? Because there is resistance in the free space as well. Now, to overcome this resistance, I will have to increase the amplitude of my voice. Now, to give you a humorous or funny example, let us say I stay at Bengaluru now. In our college, inside one particular lab where I have connected the LAN connection to my laptop and I am taking this online class. Now imagine, let us say I am not using the laptop and I am not using any of these resources. Let us say sitting in this lab, I will simply take the class. Wherever you are right now in Bengaluru or maybe in other remote places, if the space is not having any impedance, then if I speak here, sitting in the lab in the department, it must be audible to you there wherever you are, right? If space is not having impedance, then every signal should travel everywhere, anywhere, isn't it? But that does not happen that way, fortunately. Why fortunately? If it happens that way, then nobody can communicate with anybody else. If all the sounds that are produced all over the earth, if it is propagated everywhere all over the earth, no one will be able to understand what is going to happen there, because always the atmosphere will be full of all types of strange sounds which will actually be noises. Now, space is having its own impedance. That is a blessing for us. If the space is not having impedance, then naturally every sound will be audible everywhere and it will be a chaotic, noisy atmosphere always, 24 hours. Day and night always, it will be 24 hours. Why? When this side of the earth, when we have day, other side when they have night, so our sound will go there even at night. That is called Occidental side and Oriental side. Ours is Oriental side. Indian side, Asian side is called Oriental side. American side is called Occidental side. Now, when they have daytime, when we have night time, whatever sounds are produced in the Occidental side, that will transmit to the Oriental side also, if space is not having any impedance. Fortunately, space is having impedance. Space has to have impedance. Otherwise, communication is totally impossible. Okay. Now, when space is having impedance, even the space's impedance can be measured. You will learn more about it in the course called Microwaves and Radar, and you will be conducting some experiments in the next semester in the Advanced Communication Lab, where you will be using the space impedance in the formulae where you are going to measure the gain of an antenna. Gain and directivity of an antenna, which you are going to measure in the lab. There you are going to use the space impedance. Okay. So now, because of the impedance that is present in the space, there will be amplitude variations. Even though it is a wired channel, even in the wired channel there will be impedance. This you already know. Any wire is not actually a very good conductor. We are using copper as a wire for communication. Gold is better than copper. Platinum is better than copper. But we cannot use gold and platinum as communication wires. One reason is they are too much expensive. Second reason is they are not as strong as copper. Gold and platinum are not as strong as copper. The malleability and ductility of gold and platinum are much larger than copper. So As far as the strength is concerned, gold and platinum cannot be used physically that way. One more thing is, they are very much expensive. If they are very much expensive, everything will become more expensive now. Even the electrical wiring at home can become much more expensive if at all we use gold and platinum. That is one thing. Second thing is, even the wiring which we have in our home can be completely stolen by somebody else. Just a minute, I have an urgent call. Please excuse me. Okay, that was an urgent official call which I had to take. Now I am resuming my class. I was discussing about why we cannot use gold and platinum as wires at home, because everyone will steal our wires also which are at home. So that way, actually even copper wires are also being stolen at times. Whenever this electrical board people install very thick copper wires for electric supply itself, some miscreants will keep on stealing such wires also, because pure copper wire also will have some cost involved in it, and they can make an easy money by stealing that. Anyway, let me come back to the course instead of talking all other things. We cannot use gold and platinum as wires. We will be using copper only as wires. Now the copper will have its own finite resistance, due to which there will be amplitude variation, there will be attenuation. Now coming to the frequency response. As you already know, whenever a signal is transmitted, whenever it is being propagated in the channel, it will take a finite amount of time for the signal to travel through the communication channel. Even if you use optical fiber, the light also has got a finite speed, we should say. Now you may think that 3 lakh kilometers per second is the speed of light, and light is the fastest energy that is available for our communication. You may think that way. Yeah, that is fine. But even then, that also has got some finite speed, right? It is not infinite speed. Even 3 lakh kilometers per second itself is a finite speed. For example, in the olden days, they used to make satellite phone calls. International phone calls used to be through satellite. And there always used to be something called latency. Latency in the sense, when you speak, that speech will go through the radio carrier to the satellite, and it will come back as a reflected beam from the satellite, and it will reach the other place. Now, for the signal to reach to the satellite and come back to the destination, it will take some 250 milliseconds to 500 milliseconds time, approximately 0.25 seconds till 0.5 seconds time. Now that is called as latency. That is why whenever they used to make international phone calls in the previous decades, they never used to speak together always. Initially one person will speak, he will wait for some time, and it will take about half a second for the other person to receive the signal or receive the voice. Then later on he will speak. Until then this fellow will not open the mouth. They used to understand this delay, which is called latency, and that used to happen in spite of the speed of light. Imagine that the electromagnetic waves are considered to be having the speed of light itself. Radio frequency speed is taken as equivalent to the speed of light. In spite of that, we used to have latency. Now in the international phone calls nowadays, we don't have this latency, because now these phone calls are not happening through the satellites. Now they are happening through the optical fibers which are directly laid under the ocean. Complete earth is connected by means of the optical fiber cables. And now that much of distance is not there. The distance where signal used to go all the way to 36,000 kilometers up and 36,000 kilometers down. The signal used to travel 72,000 kilometers. But now in the optical fiber, it is hardly 4 to 5,000 kilometers. So that way, now when we make international phone calls, we are not experiencing that latency. But still, if you are sensitive enough, now also you can observe a small amount of delay when you make international phone calls. It will not be 250 milliseconds, but it will be at least about 50 milliseconds. If you are sensitive enough, you can observe it. That is because of the usage of the optical fiber for our communication. Now, in spite of all that, the communication channel will have frequency response variations. The reason is, as I told you, it will take a finite amount of time for the signal to propagate through the communication channel, and when it is propagating, the signal's phase may not remain accurate when it is traveling through the communication channel. Because if we take an example of a copper wire, the copper wire can be modeled as a lumped model of resistances, inductances, and capacitances. Copper wire can be modeled by means of three passive components. Now we already have studied in network analysis about the properties of inductive and capacitive reactances. Now naturally, when the communication medium is containing all these passive elements in its lumped model or distributed model, it is going to introduce different types of phase shifts into the signal. Along with that, it may always have a frequency response variation. In the sense, let us say right from 0 Hertz till let us say around 1 gigahertz. From 0 Hertz till let us say till 1 gigahertz, we use the copper wire as our channel. Now the copper wire, because of its reactive elements, may not have the same frequency response for all the range of frequencies. Now the response which is obtained for 100 kilohertz will be different from the response that is obtained for 100 megahertz. That is because of the inherent issues that are present in the communication channel. And now this is applicable even to the wireless channel also. Because even in the free space, the space is having a unevenly distributed magnetic field throughout. Which means everywhere in space, the distribution of the magnetic field is not the same. You already know that the gravity is at the highest force nearer to the surface of Earth. You already know about this factor G called acceleration due to gravity. And that is getting reduced when we go up in free space. That is why when you throw a stone up, it will come back. But when you throw a satellite up, it will not come back. It will revolve around the Earth. That means even in free space, the magnetic field is unevenly distributed, non-uniformly distributed. So naturally, even free space and even wired channels will have amplitude and frequency variations. The second point is there are variations of channel characteristics with time. Let us say we use a copper wire or an optical fiber right now. Over a period of time, the copper wire will also undergo aging. Even the optical fiber will also undergo aging. Because of the aging, the characteristics of those channels also will vary. Actually, they will deteriorate over a period of time because of aging. Anything and everything in this universe will have aging. Any material will have its own aging. Some of them will age faster, some of them will age slower. Now, this aging may not occur in the free space, but even in free space, there will be channel characteristic variation with the time. Why? In the rainy season, it will have a different characteristics. In the summer season, it will have a different characteristics. In the winter season, it will have a different characteristics. Now, in the rainy season, when the water droplets are coming down from the cloud, the water droplets themselves are going to gradually affect the propagation of the wave. Just a minute, please excuse me, I have one more call to attend now. Okay, let me continue. In the rainy season, the water droplets will affect the propagation of radio waves. And in the summer season, there will be heavy temperature in the atmosphere, and to some extent, the summer season's propagation will be somewhat better than the rainy season's propagation because there is more energy in the atmosphere. But at the same time, when there is more energy in the atmosphere, the particles will be colliding with each other due to the increased heat, and that may also introduce a noise there. And in the winter season, there is no rain and there is no heat. It will be very cold. But this cold weather may not really propagate the waves as such because of the lack of energy in the medium. This way you can understand that even the free space is subjected to all types of issues. In fact, in this universe, nothing is perfect as such. But in this universe, we are given an opportunity to actually become, to somewhat attain perfection. We human beings can really become perfect in our own way. That freedom we have. Otherwise, almost everything is imperfect that way. At the same time, there is a perfection also that way. If at all I should say philosophically, a flower can be a perfect flower when you see its beauty, when you appreciate its beauty. But at the same time, there are other flowers also which are improvised versions of the previous flowers. That way, evolution has been continuously happening in nature, or God has been planning evolution continuously. Now, let me come back from philosophy to technology again. There are variations of channel characteristics with the time, and there are non-linearities in the channel. This I have discussed in detail till now. I have discussed copper wire, I have discussed optical fiber, I have discussed free space. In addition, we will have additive and multiplicative noise injections. I will not deal with more of these noise topics. You will be studying it in the other course. But noise can be additive, noise can be multiplicative. In the sense, when the signal is going, the signal can have an addition of the noise, and the signal also can have a multiplication of the noise. You have already studied DSP, where you have come across all these concepts of multiplicative noises. I feel so, because you are going to go for some DSP processes wherein you will analyze the signal both in the time domain and in the frequency domain. Okay, you will consider in one domain you will consider it as multiplication, in the other domain you will consider it as something else. So there can be multiplicative processes, there can be additive processes. For example, inside a mixer, when a mixer is having a modulator as well as an oscillator, there when there is a modulating signal and the modulated signal, now we use the multiplicative property there because the signal is just multiplied there. Otherwise, at many times we have additive properties also. So that way there can be additive and multiplicative noise injections. Finally, there can be a fading of the signal in the channel. The fading is different from attenuation. Attenuation can be constant in the channel. That means if there is a loss of signal happening in a copper wire, that can be constant. But fading is more related to wireless channel or free space, because based on the free space's characteristics, signal can be suddenly fading. When I was in school days, my father used to tune the old radio. It was an AM radio at that time. It was not FM radio. The old radio stations, he used to tune to Radio Moscow or Radio Lahore, very distant radio stations. He used to pick up those stations at night time, because in daytime, because of the other noises, he never used to listen to those channels. But at night time, he used to access these channels: Radio Sri Lanka, Radio Moscow, Radio Lahore. They were all popular channels at that time. But at times the sound used to go away, and at times the sound used to come back. I used to ask my father what is happening there. Actually, even my father did not understand the technical things there, but my father was telling that those stations are much far away from us, so sometimes signal is lost. Later on, I understood, when I studied engineering, I understood that that itself is called as fading. Now you can think about the distance between Moscow and Bengaluru. Now, if a signal is coming through a free space to Bengaluru, now the channel, the free space in between Moscow and Bengaluru are uneven. They are not uniform, they are non-uniform, and there can be a lot of atmospheric disturbances there, due to which signal may not reach us at all at times. Such things are called fading of the signal in the channel. Now, these are all the impairments found in the physical channels, and somehow, because of the inventions of Claude Shannon, we are able to overcome all these things in one way or the other in the digital communication system. Errors are going to occur in our communication because of all these 5 factors. Now, errors are bound to occur in our communication. What we have to do at the receiver is detect the error and then correct the error. The first 3 are deterministic and the last 2 are random. The first 3, amplitude and frequency response variations, and the variations of channel characteristics with the time, and the non-linearities in the channel, they are deterministic, means if we know about the channel, we can predict. Whereas the next 2 are random. The noise that is injected in the medium, it is not predictable so easily. Even the fading that is happening in the channel is not predictable so easily. So, first they are deterministic and the last 2 are random. All these impairments are introducing errors in the transmission, and hence they limit the transmission rate. Now, the goal now is to develop a mathematical models for the communication channels. Our goal is to develop the mathematical models for the communication channels and to develop the concept of channel capacity, which represents the maximum transmission rate. We had briefly discussed about channel capacity earlier. We are going to discuss it in detail in this module now. Let me talk about discrete communication channels now. Consider a binary channel. What is a binary channel? All our present communication channels are basically binary channels. In the sense, we are going to transmit only 0 and 1. And we are going to receive also only 0 and 1. Such channel we call it as a binary channel, where the channel will have only 2 symbols, only 2 waveforms, 0 and 1. Consider a binary channel which has 2 input symbols, x1, x2, and 2 output symbols, y1, y2. I am showing you the diagram here. Now, this is a binary channel. We have x1 and x2. We can name them as x1 equals 0, x2 equals 1, because those are the 2 bits which we are going to transmit. We will get at the output y1, y2, that is 0 and 1. This is what is expected. And 2 output symbols y1, y2, that is capital X equals x1, x2, and capital Y equals y1, y2. Let us define a set called capital X and let us define a set called capital Y, which will contain these 2. Now, you may think, sir, when we transmit 0, we get 0 only, no. When you transmit 1, we will get 1 only, no. No, we may not get 0 when we transmit 0, because in the channel, if it introduces a noise, and if that noise is in the band of our communication, let us say the noise itself is in the same frequency band as our communication, then that noise will be decoded at the receiver as there is some repair work going on here, due to which there are other disturbances also. Now, today's class is a live example of what all interferences and noises can happen in between our communication. I had some official phone calls which I had to receive, and there are some repair works also here. So, you can imagine, in spite of all these things, we are supposed to have effective communication. Fine. Now, when we transmit 0, at the receiver, they will not get 0, because even when we transmit 0, the noise may be introduced in the communication channel, which may be in the same frequency band with some amplitude also, and the receiver may detect it as 1 also. That is what is this line showing here. When we transmit 0 at the receiver, we can have 1 as received. Similarly, when 1 is transmitted the receiver can have 0. Why? Because of the fading. Because of the fading, because of the additional noises. Now imagine in the communication channel, there are noises which are out of band. Now I'll give an example of 890 to 960 megahertz of GSM communication. Now if the noise is there within this particular band, then even when you transmit 0, it may come as 1. That is one case. That is this case, this particular case. One more case is, if at all there is a noise which is out of this band of 890 to 960 megahertz, and if the noise is of a larger amplitude than the signal, then what may happen is, you will transmit 1, and that will be affected by the noise which is of a different frequency, and at the receiver, your actual transmitted signal may not be received. But at the receiver, it has got a band pass filter. Now in the band pass filter, the whatever signal 1 you have transmitted, that may not be received, because the signal would have got seriously affected by the out of band noise. Noise will be anyhow filtered at the receiver because there is a band pass filter there, but the receiver will detect it as 0. Now think about only the binary channel. When we have only these two symbols, we will have all these issues. Now think about a ternary channel, think about a quaternary channel, where we use 3 symbols or 4 symbols or more. We will have more and more of such issues. But for the sake of learning, in our course, we are discussing only the binary channel. We are not going to discuss the ternary channel or the quaternary channel. But we are using ternary and quaternary channels even now. You are going to study some modulation method called QPSK, quadration phase shift keying, where there will be a phase shift of 90 degree among each symbol. So in a 360 degree waveform, you will have basically 4 waveforms with the same frequency, with the same amplitude, but only with the different phase. So there can be 4 symbols there. So those 4 waveforms can be represented using 0, 0, 0, 1, 1, 0, 1, 1. That means a single waveform will represent 2 bits now. That way, if at all we have to model such communication or such channel, it will complicate our work here. Now think about this. 0, and then I am receiving 0. I am transmitting 0, then I am receiving 0. Now I give a name of P00. Probability of transmitting 0 and receiving 0. And then probability of transmitting 0 and receiving 1. Then probability of transmitting 1 and receiving 0. And probability of transmitting 1 and receiving 1. Let me annotate. The ideal case is, we will not have this at all. The ideal case, this will not occur. Right? When you transmit a 0, you will receive a 0. When you transmit a 1, you will receive a 1. That is an ideal case. But in the practical case, these are bound to occur for all the reasons which I have been telling you till now. So now, we have to have a prediction or an assumption that there is a probability occurring as P01, there is a probability occurring that is P10. This is only with the binary channel. Now think about a ternary channel, think about a quaternary channel, where you will have 3 symbols here, you will have 4 symbols here. How will you model that particular channel? Now you will have to have different types of probabilities. Right now you have only 2 probabilities. There you will have 3 probabilities for each symbol. So you will have totally 9 such cases. Right now we have only 4 cases: P00, P01, P10, P11. In that particular case, you will have right from P00 till P22, because your symbols can be 0, 1, 2. So you will have 9 such cases. What about if you have quaternary channel? You will have 16 such cases. Now you can think about the complications. But right now we are using ternary and quaternary symbols, right? Which means what? Which means that we have automated all these processes now. Now we have central processing units inside our communication systems. We have CPUs and memories. We have enough of firmware and software inside our equipments. They will take care of all these processing algorithms. Manually, we did not do anything there. But in our course, we are selecting only the binary symmetric channel for our discussion because here we are going to work out manually for our sake of understanding. I hope you have got this concept of 4 probabilities. Let me proceed now. Due to the errors in the channel, the output symbol may be different from the input symbol during some symbol intervals. As errors occur in a random fashion, let us assign probabilities to the possibilities assuming a memoryless channel. That means, let me have this capital P, probability of x equals 0, because it is going to be now a transition probability, it is going to be a joint probability. So, P0 being transmitted and P0 being received. This T stands for transmission, R stands for reception. Similarly, probability of x equals 1 is P1 being transmitted and P1 being received. Also, the transition probability is Pij is P of y equals j when x equals I. That is P01 and P10. That is what we discussed in the earlier diagram. Now, based on these things, now we can have an expression P0R and P1R can be expressed as P0R. That means 0 being received at the destination. Its probability is 0 being transmitted into 0 being transmitted and 0 being received. Then plus P probability of 1 being transmitted and 1 became 0 because of the errors. You have to carefully understand this expression. Probability of 0 being received is probability of 0 being transmitted and 0, 0 is going in the channel. 0 is transmitted, 0 is going in the channel. Now, along with that, if 1 is transmitted because of noise, that 1 may become 0. Now, that is P10. Now, this P00 and P10 is what? It is a joint probability, or let us say it's a transition probability in this particular context. Now, P00, P10 is a transition probability, whereas P0R itself is a joint probability. We already know these definitions, right? When any events are statistically dependent, then the probability is multiplied. And when any events are statistically independent, then the probabilities are added. You will have to always remember this basic concept. Now, these two probabilities are added because they are statistically independent. But these two probabilities are multiplied because they are statistically dependent. 0 being received and 0 being transmitted. That is what we want here. Again, 1 being transmitted, 0 being received. That is what is expected here at the receiver. So now, similarly, probability of 1 being received is equivalent to probability of 0 being transmitted and then 1 being going out to the destination, plus probability of 1 being transmitted and 1 being received at the destination. So that way we have two expressions now. One is P0R equals P0T into P00 plus P1T into P10. Next, P1R equals P0T into P01 plus P1T into P11. Now, you may think that why do we have this P0T and P0R? Is there any probability of 0 being transmitted? There is, because in the communication system at the information source, we have 0 and 1, right? So, the probability of 0 going is 50% and probability of 1 going is 50%, right? It is like tossing of a coin. When you toss a coin, either it is head or it is tail, which means probability of head is 50%, probability of tail is 50% if the coin is a fair coin. In the same way, if the information source is a fair information source, P0T will be 50% and P1T also will be 50%. We are going to use all these assumptions or these results in future. So now, if P00 equals P11 equals P, then the channel is called as binary symmetric channel. which means what? As I told you, 0 being transmitted and 0 being received. If it is equivalent to 1 being transmitted and 1 being received, then we can say that the channel is symmetric, and in such a case we call it as a binary symmetric channel, means it can equally propagate 0 and 1. That is how the channel is characterized. Now finally, the probability of error is given as the probability of error. We don't want to have a error in communication, but error is bound to occur. Now the probability of error can be expressed as PE equals probability of y is unequal to x, which means probability of x is transmitted as 0, y is received as 1, plus probability of x is transmitted as 1 and y is received as 0. Now expressing this in conditional probabilities, we have PE equals P of x equals 0 into P of y equals 1 condition to x equals 0, plus P of x equals 1 into P of y equals 0 condition to x equals 1. Now for this one, we can write an expression PE equals P0t into P01 plus P1t into P10, which means 0 is transmitted, 1 is received, and 1 is transmitted, 0 is received. These two are mutually independent, so there is an addition, but these two are mutually dependent, so they are multiplied. This is the error. I'll go back to the previous one. You can see this here. Here we did not consider the error because 0 is received, 0 transmitted, 0 is obtained, 0 is obtained. That is how we thought. But we did not consider the error in these two expressions. Now we can express the error in this fashion as PE equals P0t into P01 plus P1t into P10. Now the difference 1 minus PE is the average probability of correct reception. If at all we find the probability of error, which is always between 0 and 1 now. If PE is 0, then communication is 100% successful. There is no error. If PE is 1 means communication is totally gone. There is no signal which is received or decoded correctly at the receiver. Now PE will remain in between 0 and 1 always. Ideally we want PE to be 0. Total failure of communication is when PE equals 1. But in between them it exists. So the difference 1 minus PE is the average probability of correct reception. Let me stop here and let me continue again in the next class. I will be taking the next class immediately in the 4th hour. Let me end this meeting as of now.